And this is 2011. Okay, so just 2 years ago. I'm pretty confident that we're going to have an acid and base, but again, I don't get to make these questions up. If I were designing the exam, I would have an acid and base question for number 1. All right. Let's see. We have 3 different beakers here: beaker 1, beaker 2, beaker 3, and they have HCl, NH3, and NH4Cl. Now, you should be able to recognize. Okay, actually, let me ask you this because it was on our last mock exam. What is ammonia? NH3, good, know that. What is vinegar? Acetic acid, know that, okay? So knowing, ooh, that wasn't good. Well, I made more. There's a post-it note, yeah, they should be fired. All right, so what do we have in this beaker? Don't tell me HCl. Strong acid. Weak base, okay? And wherever ammonia goes, generally speaking, ammonium is nearby, okay? Remember that. They're like a beautiful married couple. And then over here we have our ammonium chloride. So this could be considered our salt, okay? So we have a strong acid, a weak base, and a salt. Okay, recognize that. Part A says determine the pH of the solution in beaker 1. Oh my God, that's so easy. Well, how do you do it? Pray to the chemistry gods we get a question like that. pH.
We don't smack you upside the head when you get it wrong.
Negative log of 0.1, right? This should be a non-calculator question. Okay. Can everybody do that in their head? No? Okay, well here, I'll give you another one. What is the pH for the negative log of 1 times 10 to the negative 5? 5, very good. Okay. Here's another one. pH is equal to negative log of 1.0 times 10 to the negative 23. 23, you got it. Okay. All right, so first part's done. Part B says in beaker 2, the reaction of ammonia with water and ammonium and hydroxide occurs. The value of the Kb for the ammonia is 1.8 times 10 to the negative 5 at 25 degrees. Right? Man, we need a question like this tomorrow or Monday. Write the expression. You done? Those are 2 easy points right there. Kb. Where the equation go? There it is. So NH4. Again, make sure that in your expression, hydrogen or hydroxide is always on top. Okay? And by doing that, you're making sure that they're on the product side, the hydrogen or hydroxide. And if you wanted, you could put just dazzle them, but that's not required. Okay. Calculate the OH in beaker 2. How would you do that? Ice chart it, very good. Okay, so in beaker 2, we have our equation. And do we know any information? Oh yeah, we have a 0.1 for this. Yeah.
Going from NH4 to NH3.
Oh, my bad, my bad. That's a 3. Thank you. NH3. So what is my initial concentration for the NH3? 0.1. Okay. And my initial for the ammonium, 0, very good. Why is it 0 and not 0.1? Because it says 0.1 here. Beaker 2, very good. So read the question. Okay, and the OH is also 0, not approximately 0, it is 0. Then we'll minus that, we'll add that, 0.1 minus that. So all that fun stuff. Okay, you have your expression, plug them in. God, we really want this question. This would be awesome. Is equal to and can we use 5%? Absolutely. So 1.8 times 10 to the negative 5 times the 0.1 is equal to our KB, which is 1. Looking for OH. No? Sorry. So x squared is equal to 1.8 times 10 to the negative 6. Is that right? Yeah. And then x square root of that. So like 1.3, 4 times 10 to the negative 6, 3. And did it just ask for the concentration? Yeah, so that's where you'd stop. Don't go and find the pH if it's not asking for it. Okay. Everybody good with that?
Just to be safe, should we rewrite the KB expression or
No. Once you've written the KB anywhere on your sheet, you're solid. Okay. Just make sure that you plug it in. Yeah, Nolan.
Do you have to show what x squared is, or can you just go straight and say x equals this?
Show this at least before you go to this. Oh, show this before you go to this. At least show that. Okay.
Do you have to include the minus x, or can you just automatically?
If you're using 5% as a courtesy, I would show it before I dropped it. So like I'm a bad example in this example. All right. Let's see, where are we at? Double I? No, we did that one. So C, is that where we're at? Okay, in beaker 3, the reaction of ammonia plus water yields the ammonia and hydrogen ions that occur. Calculate the Ka for the ammonium at 25 degrees. Okay. How would we do that? Yes, Megan?
I was thinking 1.0 times 10 to the negative 14.
Very nice. So Kw is equal to Ka times Kb. You already have the Kb for ammonium, for ammonia. To find the ammonium at the same temperature, do your Kw. Okay, so in this case we're looking for Ka, which is equal to Kw over Kb. Okay, no ice chart. And what was it? 6. What the heck is it? Oh, 1.8, sorry.
Is the KW given to us on our?
Yes. I don't have my equation sheet, but it's under the acid and base section. Okay. It's also with, does anybody have their equation sheet? I don't know if I have one. Let's see. I think I have one here. So under the equilibrium section, where are you? Right here. So here. Okay, it's kind of like in 3 things are going along with it: the hydrogen hydroxide, Ka and Kb. Yeah, know where everything's at on your equation sheet so you're not frantically searching for it. All right, so Megan, would you come up with an answer there?
Oh, I don't have my calculator.
Perfect. Did anybody come up with a number?
5.566.
Negative 10. Good. Excellent. Okay. 3 should be there since we had 3. Where are you? Oh, yeah. So, in this case, it should be 5.6. Okay. Everybody see that or hear that question? That's a good one. Sig figs. Since they gave us 1.8, just be cognizant of something like that. Hey, Ami, did you grab a sheet? Okay. So, since there's 1.8, just if you got a heads up, just round it to 2 sig figs in that case. Okay. All right. I think we're here. The contents of beaker 2 are poured into beaker 3. So 2 and 3 are mixed together, which is nice. We like that. The resulting solution is stirred. Assume that the volumes are additive. Calculate the pH of the resulting solution. So what are we doing when we mix beaker 2 and beaker 3 together? What are we creating? A buffer. Okay. So you're actually creating your buffer, and then we're going to be asked some questions about it. Okay. So how would we be able to determine the pH if we mix those two together? Well, we know the concentration for beaker 2 and beaker 3. And when you do an ice chart, actually, just at the equivalence point is enough. Okay, so okay, because again, nothing's going to change. So we have our 0.1, and then we have our 0.1. And then we don't know how much of we have some hydroxide, but it's not 0, so it's really small. Okay. That's actually what we're kind of looking for. Okay. Now, another way you could do it, if you didn't want to do that, but you wanted to do this is also okay. Okay, so the options are open for you, where we have. Okay, and which one do you want to do? The second one? Why? Because we know the Ka. That's fine. And you also have the Kb, so it's up to you. Yeah.
The volume's not changed, this is the volume's, or the polarity's not changed, this is the volume's additive. It's 0.1 per 25 milliliters.
No, wait a minute. Ew, that's ugly. Well, shoot. The volumes are, You still have our 0.1. Crap. I'm drawing a blank here. Ask the question again.
Since it's 0.1 molarity for 25 milliliters, but the volume's additive is 50 milliliters, but the molarity change as well.
Did they give us volumes here?
Yep. Each of 3 beakers.
Oh, there it is. Yeah, okay. Yeah, okay. There we go. Maxwell it is? Good.
Danny, isn't this one we talked about before?
I think so, yeah.
Go ahead, lead it. So well, tell me how we're going to do it. I like it, where you're going here.
I don't remember.
Seriously, come on.
I know.
Go ahead.
Just add the volumes and then do the molarity.
Yeah, so find the number of moles based on your total volume, right? All right, so let's flip that around. So we have our, let's see, the 0.1, I'm sorry, we have 50 milliliters total. Yeah, 2011. 2011, section A, part A. Where's the point? Hold on here. 50 milliliters. have a 0.1 molar solution. And we have 50 milliliters. Actually, it'll work for either. Do that both times there.
What if you start with 25?
What's that?
What if you start with 25, and we have 25 initially, and we divide it?
That's true. Thank you. See, hey, you guys are on this.
Go Team Blast.
Times 0.1, so we've got 0.0025 moles. And that's both for the NH3 and the NH4, correct? Okay. All right, so now we have our new concentrations for these over 50 milliliters. So divided by 0.05. Oh, big M. All right, so now we have our concentration for each of those, which means that we get to now do our ice chart. And which one did we want to go with? Well, you can pick either, actually. So we have our 0.05. There we go. You know what's dirty about that? Did we need to do this? Why? Say cancel out. That is stinking bad. All right, let me write the expression. So we have our NH4. You know, College Board should be shot. That is a dirty, stinking question.
No, it's not.
Yeah, it is.
I love it.
Because I left it as 0.1, and I'm still going to get the same blanket answer. Mm-hmm. Yep. All right, so goodbye, same. And your hydroxide concentration is equal to 1.8 times 10 negative 5. So I guess a good heads up would have been nice. So we'll find the POH, negative log. And actually, or to find it. Is it asking for the pH? Okay, well, let's be smart about this. Let's go 14 minus negative log of 1.8. Why do you have so many X's?
Because these two concentrations have to be the same, right? And the
No.
concentration of
They're-
ammonia-
Well, the hydrogen we're looking for.
Right.
Yeah. Yeah, we have a small amount. We have a hydrogen, we have our ammonium and our ammonia, so we're looking for the hydrogen, yeah. So, 14 minus negative log. Yeah, if it were just one thing, that would be. So anybody get 9.26-ish? Yay, nay?
Okay, did we have to do all that, or could we have just said they're going to cancel out and then just go straight to that? Because I feel like to save time.
That is a great question. Because the way that I worked it out, I left it as 0.1 and got the same stinking answer. I guess.
Would they count you off if you didn't show that step? Because it really is kind of irrelevant to the actual problem.
You would have to show, you would need to show this as well as this. So to do what Danny said, yeah. I think the reason why I didn't do it is because back when I first worked it out, I recognized that, and here sitting in front of everybody, it's like, I haven't got enough Diet Coke in me yet. I don't know. All right, is that the last one, or do we have another one? Oh, here we go. Part D. Wait a minute. Yeah, part D, right? The contents in beaker 1 are... Did we do this already? Oh no, the contents in beaker 1 are poured into the solution made in part C double I. The resulting solution is stirred. Assume the volumes are additive. Is the resulting solution an effective buffer? And it says justify your answer. So justify means you can either do math or you can write a sentence. Okay? So is it an effective buffer? I'm going to leave it up to you guys. You tell me. Yay or nay? All right. Let's do this. Let's say that we've got some ammonium and some ammonia. Okay? So here's what you have initially. Okay? So what's going to happen here? It's going to absorb it all, right? Okay? So we'll add it on this side. So we get this, this, and this. All right. So is that an effective buffer?
I have a question.
Yes.
Why does NH3 have a plus beside it?
I think I was doing plus twice here.
Okay.
I know. An effective buffer. What does an effective buffer mean?
It resists pH change well.
It resists a large change in pH. So will the pH change quite a bit here? Oh yeah. We're essentially going from a pH of 1 to, wow. Okay. It's really going to change. So is this an effective buffer? No. Was the buffer capacity exceeded? That's kind of a dirty question, actually. I think we hit the point where we're about ready to exceed it. Yeah, Niles. Now say that again.
Yeah, so like, why are you using the 4 and 3 ones?
Okay. So what we did in the part before, we mixed these two together. So we made a buffer solution because we have the ammonia and then the salt of the weak base. And then we poured beaker 1 into the contents of the beaker that we mixed together from here. So we mixed these two together into a beaker, and then so we had that beaker with 50 milliliters, and then we dumped that into there. Okay, so we built our buffer system, and then we added the strong acid to the buffer to see, hey, is this a good idea? And that's what we're piggybacking off here. Okay. Yeah.
So we're just using the information from the two beakers, right? Beaker 2 and beaker 3, and those are the concentrations, and then we subtract that.
Correct.
Add that. Okay.
Perfect. Yeah, Ami. This one? That one?
Why'd you subtract 2.1 from the concentration of H plus?
Okay. So what we have here, ammonia is our weak base. The hydrogen ions from the HCl is our strong acid. So we always want to find out which one's smaller and that one goes to 0. Well, in this case, they're both. Okay. All right, and then double I. Ooh, that's a good one. That looks innocent. Calculate the final ammonium concentration. The resulting solution made at 25 degrees. Okay. How should we attack that? How should we attack that one? Alex, you just showed up. How would we attack that? Just Just because you're out doing a workout doesn't mean that you're gonna. All right, well, let's see here. Getting a lot of paper up here. If we mix all the solutions together, is it safe to say that the ammonia, the ammonium, and the HCl would all have the same number of moles initially? Okay. So we have 25 milliliters, like what we just calculated earlier. Okay. Which is 0.025 moles of each. Okay. So they each have 0.0025 moles. And what's our total volume here?
Oh, no.
We have 25 of that, 25 of that, 25 of that. 75 milliliters. Okay. So that equals 0.075 liters. Okay. And so then we can find out that, okay, let's do a, get you out of the way for a second.
Mr. Craig, would
Yeah.
you have to do the 25 milliliters to mole stuff the way you already did it? 'Cause
We did it earlier.
Yeah.
No, if you've already done that work, then you're good for that.
Okay.
Okay, so you don't have to repeat efforts. Okay, so actually this looks pretty much the same as what we did up above. Plus our hydrogen, which is this. And again, there's more than one way of doing this. So our initial I love Elmo. Not. So this looks very familiar. And then, since we have our moles of ammonium there, let's take your 0.005 moles and divide by our 75 milliliters. And I think that equals 667. Okay. So and I would be willing to bet that you don't have to show all those steps. Okay. All right. Courtney, we worked out, and I have it recorded, so I'll post that on later. All right. Any other questions? Okay, so I went through a titration, went through a buffer question. What other questions do you have about acids and bases, since most likely that's going to be question 1? Yeah?
That part DI, about it being, not being an effective buffer.
Oh, okay.
Can you explain that again?
All right. Since, let's see here, where'd we go? Back to this guy. All right, initially, if we said, okay, what? What happened? Oh, okay. Since we had our pH for our solution was something at this initially. If the pH changes by any great amount, now, again, when I say any great amount, I'm thinking more than 1, 1.5 as a pH. 2 would really, really be a lot. So our pH would change by more than that, going from here to here. Because again, the hydrogen, when that's in the solution, is going to have a pH that's really, really low initially. And since we are not able to have a sufficient amount, or actually we don't have any at the end, at the equilibrium step here, then that's not a very good buffer. Actually, that's a pretty poor buffer. So when we add something, a strong acid or strong base, we don't want to use up all of our weak whatever in our salt that's associated with that. Okay. Yeah.
So it'd be a good buffer if the concentration of the ammonia was greater than 0.1 to begin with.
If it were like 0.2, yes, or much higher, that would leave a substantial amount. Yeah, what a buffer doesn't want to do is be completely consumed, and that's what happened here.
So if we were to ask, how can we make the buffer stronger for some question, we would just say we could add ammonia